Hello everyone, welcome to Prince Expository YouTube channel. Today we are going to learn about Introduction to Finite Element Method. The Finite Element Method FEM is a widely used method for numerically solving differential equations arising in engineering and mathematical modeling. When it comes to the history of this finite element method, it is very difficult to quote a date of the invention of the finite element method. The method originated from the need to solve complex elasticity and structural analysis problems in civil and aeronautical engineering. Its development can be traced back to the work done by many eminent people in the early 1940s. Now let us quickly get into the introduction of finite element method. The finite element analysis or finite element method is a numerical method for solving problems of engineering and mathematical physics. Useful for problems with complicated geometries, loadings, and material properties where analytical solutions cannot be obtained so easily. Now, see the basic definition of FEA or FEM. So, this is a numerical method and can be represented in the form of a mathematical representation of an actual problem. This numerical method is an approximate method. The finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing. FEM, three letters. F stands for finite, E stands for element, M stands for method. F infinite defines as it reduces the degrees of freedom from infinite to finite. E element, all the calculations are made at a limited number of points known as nodes. The entity joining nodes and forming a specific shape such as quadrilateral or triangular is known as an element. M indicates method. There are three methods to solve any engineering problem, and this particularly finite element analysis belongs to the numerical method category. Engineering problem can be obtained solution in many ways. Any engineering problem can be obtained, be it from simple to complex, we can get the solution. So here are some of the methods that we can follow for getting the solution for an engineering problem. The first one is analytical method, second one numerical method, and the third one experimental method. Analytical method is a classical method which gives 100% accurate results. It is also called as closed form solution, which is applicable only for the simple problems like cantilever, simply supported beams, etc. Another method is numerical method. It is a mathematical representation. It is an approximate method, and in numerical method, few assumptions will be made. Many of the real life complex problems can be solved using this numerical method. The results obtained from this method cannot be blindly believed. Certain results must be validated by experiments or an analytical method. Some of the numerical methods comes under this category, namely FEM, BEM, FEM and FDM, etc. The third method is experimental method. Experimental method needs actual measurement. It is a time-consuming method wherein which we need an expensive setup to measure. Applicable only if physical prototype is available. Here also in this method, results cannot be believed blindly and a minimum of 3 to 5 prototypes must be tested. There are so many other gauges, sensors, meters will be used for the measurement in this experimental method. Now, as we have seen in the previous slide, there are different numerical methods. The first one is finite element method, and this finite element method is a popular numerical technique used to determine the approximate solution for a partial differential equations. There are so many applications which are under FEA, namely linear, non-linear, buckling, thermal, dynamic, and fatigue analysis, etc. The second numerical method is BEM, and it stands boundary element method, which is the most powerful and efficient technique to solve acoustic and other problems. Just like FEA, it also requires nodes and elements, but it only considers the outer boundary of the domain. So when the problem is of a volume, only the outer surfaces are considered. If the domain is of the area, then only the outer periphery is considered. The third method is finite volume method. This method, representing and evaluating partial differential equations as algebraic equations, method is used in many computational fluid dynamics software packages. This finite element method, some of the areas include computational fluid dynamics, computational electromagnet. Next method is finite different methods. It uses Taylor's series to convert a differential equation to an algebraic equation. In the conversion process, higher order terms are neglected. It is also used in combination with boundary element method and finite volume method to solve thermal problems and also CFD coupled problems. Let us see in this present slide how FEA plays a prominent role in product life cycle. Now in the product life cycle, it starts with product specifications, conceptual design, ergonomics and aesthetics, standards, detailed design, prototype development, testing, simulation, design for manufacture, design for assembly, and finally drafting. So in this present slide, we can see the prominence of FEA in product life cycle is under simulation. Now let us look at the next slide so that we can easily understand the real definition of finite element analysis. In this figure that is shown to you in the slide, a problem is considered, and this problem is divided into small segments, and these small problems can be easily obtained a solution, and finally these small solved problems if we can able to reassemble, and then we'll be getting the final picture of the problem solution. Main important part in FEM is discretization of problem. Discretization is modeling a body by dividing it into an equivalent system of finite elements interconnected at a finite number of points on each element called nodes. Meshing is nothing but the discretization of continuous system with infinite degrees of freedom to finite degrees of freedom. Here you can see the three images that were shown in this slide. Let us consider an object, and this object is discretized into equivalent finite elements, particularly three finite triangular elements. Now these three elements were connected or interconnected with a finite number of points called nodes. Basic principles of FEM includes, first of all, appropriate discretization. Why we have to follow this appropriate discretization? Because this appropriate discretization tries to represent the essence of the physical object with associated physical properties and application of loads. And the main features of this discretized model were nodes and elements. Now in this slide you can see there are two images. First image is showing you the number of nodes are infinite. Degrees of freedom per node is 6. Because of infinite number of nodes, infinite number of equations will be obtained. And it is very difficult for us to solve the problem. Now if we see a uniformity or an appropriate discretization has been done in the second figure with number of nodes 9, degrees of freedom 6, and of course total equations we will be getting as 54, wherein which we can easily solve this problem. The total degrees of freedom for a given mesh model is equal to the number of nodes multiplied by the number of degrees of freedom per node. Now let us see various types of the elements that is formed because of the discretization. There are one-dimensional elements, two-dimensional elements, three-dimensional and other dimensions. One-dimensional is nothing but one of the dimension is very large in comparison to the other two. And line is the element shape under this category. Rod, bar, beam, pipe, etc. are the element shapes. And practical uses comes under long shafts, beams, pin joint, etc. Two-dimensional elements are nothing but two of the dimensions are very large in comparison to the third one. Quad, tria, arc tria, etc. comes under element shapes. Thin shell, plane, membrane, plane stress, plane strain, asymmetric solid, etc. comes under the element type in this 2D. So various practical uses include sheet metal parts, plastic components, instrument panels, dashboards, etc. Three-dimensional elements are nothing but all dimensions are comparable. Tetra, penta, hex, pyramid comes under the element shapes. Solid is the element type and there are so many practical uses, namely transmission casing, engine block, crankshaft, etc. In addition to this one-dimensional, two-dimensional, three-dimensional, there are mass elements, point elements, etc. Let us look into that. Spring, damper are certain elements with translational rotational stiffness, damper with damping coefficient, etc. Now let us just focus upon the application areas of FEM. FEM has a widespread in various applications, namely mechanical, aerospace, civil, automotive, structural, stress analysis, static, dynamic, linear or non-linear, fluid flow, heat transfer, electromagnetic fields, soil mechanics, acoustics, biomechanics. The following are the application areas are not only the application areas of FEM, there are many more areas which I didn't include in this slide. With this, I will just end up the introduction to FEM. We'll meet in the other class with the continuation topics. Thank you.